Hey, welcome back to Math with Patrick and Quill. Today is November 29th, and we're solving problem 333 from the Daily Epsilon calendar. And the answer should be 29 because that's today's date. So we need to find the sum of the denominators of the Egyptian fraction expansion of 41/55. So before reading this problem, I've actually never heard of this before, an Egyptian fraction expansion. And the idea behind this is that, well, actually, historically, I believe the Egyptians maybe invented this way of thinking about fractions. And the way to write this expansion is basically we're going to have 1 over some kind of denominator plus 1 over another denominator, like a different number, plus 1 over another denominator, plus however many of these fractions we need to get the target value. The idea is that the numerator is always 1 and the denominators are distinct. And I've never thought of this before, so I had to look up a few strategies. One thing I want to share though is just to see what happens if we start over here and get something on the left. Like, for example, we could try adding 1/2 and 1/3. That would be a totally valid Egyptian fraction expansion. To do this, I would find a common denominator of 6. I would get the correct numerators, and then now I have 5/6. So if we started with 5/6, then we could go back to 1/2 plus 1/3 to get an Egyptian fraction expansion. So one thing that seems useful is if we're starting over here with 41/55, maybe I would want to start by splitting up the fraction into multiple and just seeing what happens to the numerators. Now, there is a thing called partial fraction decomposition, where if you start with any fraction, you can always split it up by using factors of the denominator. Always is a little bit wrong, maybe. Like if our denominator were, say, a square number, then here I would have to choose the number itself and then the square root of that number. So this is kind of a special case of fraction decomposition. But in this case, where 55 is factorable and it's not a square number, rather it's square free, I know that we can split this 55 into a 5 and 11, the factors of 55, and we just need to figure out what these new numerators should be. Now, to do this, we could just multiply both sides of this equation by 55. We will get 41 equals 11a because like the 5's cancel out in 55 and 5. And then we will get 5 times b. Now, this is a little tricky, just given that there's infinite solutions here. However, knowing that we were working with fractions, we know that a and b should be integers, so it's not that bad. I can kind of clearly see that a should be 1 right here, because then we're left over with the number 30 to get to 41, and 30 is a multiple of 5. Now, if I plugged in anything else for a, like say a 3, I would get 33 over here. I would need this number, for example, to be 8, and that's just not a multiple of 5. So with a little bit of guess and check and just kind of guessing the first obvious number, a is 1, and then 5b must be 30, and so b itself must be 6. So this gives us one of our fractions for our Egyptian fraction expansion, because now that we know that a is 1, we have 1/5. This is kind of fitting the bill of the definition from before, but we do have 6 over 11, and that's not what we wanted. We wanted a 1 in the numerator. So here's a strategy specifically for Egyptian fraction expansions. Let me write some kind of identity here first with fractions, and I'll prove it in a sec. I believe if we have something like 2 over x, we can say that this is equal to, let's do 2 over, I think it's x plus 1, plus 2 over x times x plus 1. And now this might seem like a pretty convoluted mess, but let's just multiply both sides by, I think, x times x plus 1. This is kind of familiar to me, multiplying both sides by 55 earlier, actually. Then I'll also multiply both sides here by x times x plus 1. Again, I'm only doing this to more readily show that this is actually a true equation. On the left side, we get 2. these x's cancel, so then we have 2 times x plus 1. And then on the right side, the x plus 1 and that x plus 1 cancel, so we get 2x. And then this and that cancel entirely, so we just get 2x plus 2. Now here, it's a lot easier for me to see that we could just distribute the 2 and confirm that these two values are the same. And so going back to this representation, I'm more comfortable saying that, yep, these two things were equal. I guess with the caveat that this x shouldn't be 0, nor -1, or else these kind of denominators would be 0. Fortunately, I don't think we're going to be running into a 0 or a -1 anytime soon, because I'm going to try to use this on the number 6/11ths. So let's take 6/11ths. If I factor out a 3 for some reason, so 3 times 2/11ths, now I'm able to parse out 2/11ths as something new. So let me keep this 3 the same. And then using this kind of identity here, 2 over x, x being 11, should be the same thing as 2 over 12, and then plus 2 over 11 times 12. Now we can simplify those on the inside a little bit. We do get 3 times and then 1/6, and then plus, let's see, the 2 and the 12 can cancel out to get a 6 on the bottom, so we have 1 over 66. Let's maybe distribute that 3, and maybe we're getting a little bit lucky here, but we can also simplify these fractions to get 1/2, and then 1 over 22. And both of these numbers are satisfying what we need for the Egyptian fraction expansion. So this 1/2 plus 1 over 22 should be the same as 6/11ths. And then as long as we just add 1/5 to that, we should get back to our target number. So our answer today, well, not yet, but the almost answer is going to be 1/2 plus 1/5 plus 1 over 22. And we can confirm that we're right by finally adding up the denominators in this expansion. And we get 22 plus 7, which is 29. And that's today's date. So there we go. This is at least one example of finding the Egyptian fraction expansion of just some kind of fraction here. Maybe there's other strategies for different kinds of numbers. Maybe some numbers are easier or harder than others. I'm not sure. But we at least can prove that 29 does make sense for today's problem. So I'm all done for now. Thanks for watching, and I'll see you tomorrow. Bye.